Hello, and welcome back to Introduction to Algorithms. Today, we're starting with Chapter 2, Search Problems and Search Algorithms. Last time, I already showed you the overview of Chapter 2, so let me recall it for your convenience and benefit. Chapter 2. Chapter 2, we're going to talk first about linear search. Then we talk about neighbor search, which is both a search problem and a search algorithm. We talk about binary search, talk about uniqueness, which is a variant, if you like, of searching. We'll talk about hashing-based algorithms for the uniqueness problem. We'll talk about order statistics, which is a generalization of the median problem. Median, as you recall, means find an element where half the other elements are smaller and half the other elements are larger. So that's median, and order statistics generalize that like 30% smaller and 70% larger, for example. So that's also a variant of the search problem. Then we talk about geometric search problems, starting with the one-dimensional case, searching and counting, which is also generalization of search problem, and the two-dimensional case, searching and counting. And I leave it to a lecture on computational geometry to generalize that to high dimension and to consider other geometric search problems. So this is a hidden cross promotion for lectures on computational geometry beyond the purpose of this introductory course in algorithm. And also in chapter 2, we'll follow the paradigms, the virtues of computer science, emphasizing the importance and elaborating on specifying the problem precisely first, then indicating which primitives we're going to use in our algorithms, what is the semantics of these primitives, and what is the cost of these primitives. Only then we start designing algorithms as opposed to coding. We will analyze these algorithms, asymptotical cost. We'll mostly focus on runtime cost, but we'll see here that runtime only may not be the most important part. Maybe also sometimes memory will be relevant. And I'll leave it again to another advanced course on design and analysis of algorithms to consider further measures of cost beyond running time, beyond memory, such as, for example, a communication volume. And we'll briefly touch the question of optimality of the algorithms in this section. Instead, leave that to further later section. So that being said, let's start with talking about linear search. And the thing is, you all know linear search as an algorithm. But what I want to do here is to emphasize the importance and to illustrate how to specify a problem and the issue about the primitives we're using and the computational cost assigned to the primitives. And here we start this with a very basic example, namely linear search. So specification, we're going to fix just a set, only a set. That's a set of elements that will be we will be searching among and searching for. So the input is a finite sequence of elements from that set, as well as the length of that sequence, which is an integer. And just to give you an example application, imagine that X is the set of student records of some university, and we want to find some student based on the student record. So that means X is a maybe very complicated set, capturing all the fields in the student record, such as name, date of birth, and semester, major, and so on. So, and technically in machine or programming language, the input of a finite sequence is commonly proceeds and use an array. Further input is an element y. That is, for example, the student we're looking for among the existing students enrolled, among the x1 up to xn. So the student we're looking for is again an element from that set x, and we're following our paradigm of abstraction and generalizing that to an arbitrary set x. So that's a input specification. Output is we're looking for an index of in that array, in that input sequence, where the student y we're looking for occurs. That's a student, or more generally, if that's an element of the set x. If such an index exists, if no such index exists, if the element y does not occur in the input sequence, then the specification asks to indicate that in the resulting value integer, namely the integer 0, should indicate that y does not occur in the input sequence. And observe that 0 serves and can be used for such a unique indicator, because in the case that y does exist, then the output will be some integer, some positive integer from 1 to n. So 0 is kind of really available for this indication. And you already see that rigorously specifying a problem is maybe a little bit delicate, but also very important. Otherwise, later it's a high chance of misunderstanding, particularly when there are several parties involved in designing algorithms for one part and using these algorithms by a different group. So one further case I'd like to emphasize here is that if element y occurs repeatedly in the input sequence, then that means there are several possible return indices n, and our specification says that any such index is suitable. We don't require the least or anything. So now we've really fully specified the problem that we want to solve algorithmically. And next step, recall, is to clarify which primitives we can use in designing such algorithms. So, for example, if the general search primitive is permitted, then there's no point in designing an algorithm, right? Then we just evoke the search primitive. So the interesting case here is when we really only can compare individual elements. And to this end, let us agree that we have access to individual elements from the array, from the finite sequence, formalized as a mapping from the index, which is a natural number, positive integer, to the element at the stored at that position in the array, an element from x. So this is a formal mapping. And the other primitive that we're going to use, and now this comparison, more precisely, comparison for equality and its logical complement for non-equality. So we're going to make a first assumption by assigning cost 1 to each of them. So that means we're going to ignore such aspects as the size of the elements that we're comparing here, or the magnitude of the integer that enters in the for the array access. So this is the first approximation when we design and analyze algorithm for the search problem. Later, one might want to have a closer look that does take into account the magnitude of the integer, the binary length, and the size of the data being compared. But for now, and since this is only for illustrative purposes, let's leave it at that, because you all know the algorithm, right? So this is more to illustrate the and exemplify specification and the choice of primitives, their semantics, and their cost. We're going to allow for another type of primitives, namely integer arithmetic on indices, right? So there's no point in having arithmetic addition or subtraction on elements from the set X because it's a generic set, like a set of student records. You cannot add 2 student records or multiply them. But indices, since these are natural numbers, they can be, it makes sense to increment them, to add them, or to scale them. So we make that explicit and charge cost 1 to them. And then the algorithm is kind of trivial. You all know the algorithm walks through the array one by one, and at each position check whether the element stored at that array position agrees with the element we're looking for. If so, then stop searching, return that index we have found the element. We're in the first case. And otherwise, if we have run through the entire array without finding the element, then that means that the element does not occur at all, and the algorithm thus will return the indicator index 0. So that's our linear search algorithm. The algorithm, again, that we emphasize that is trivial. Maybe the more interesting part is how we have applied our virtues of specification and of agreeing on the primitives, their semantics, and their cost. Semantics, for example, meaning we consider here mathematical integer arithmetic, not machine integer arithmetic, where for perhaps wraparounds can occur. Subtle but important aspect here. Okay, so that was easy. Let's just complete. The algorithm is obviously correct, right? And the computational cost, the runtime, is linear because the algorithm walks through the entire array, and that's optimal. Any algorithm for the search problem cannot even miss looking at any element in the array. It has to read the entire input array. So O of n is optimal. End of story. Let's move on. Move on to maybe more interesting problem, namely the problem of neighborhood searching. Neighborhood searching, we want to refine the answer of the algorithm in the case that the element does not occur in the sequence. So in the previous specification required that in this case only the indicator 0 be returned, indicating that the element is not in the array. But here we want to strengthen that specification. If the element does not occur in the input array, then we want to return some neighbor in the array that is in a sense close to the element we're looking for. And then based on that information, it's easy to compare that this close element is still different from the one we're looking for and thus distinct. So it's easy to recover the previous indicator, but now the specification will require to provide more detailed information. Let me proceed by explaining the specification of this problem. And here we strengthen the mathematical hypothesis. Namely, we're going to talk about searching data from a set X, which is equipped with a total order. So now it makes mathematical sense by hypothesis to compare elements from the set with respect to being larger or smaller. Any two elements can be compared. That's a definition of total order, as you recall from discrete mathematics, the required background for this course. Whereas in previous case, we were only able to compare two elements for being equal or unequal. So to return to my example of student records, you can say if these two student records coincide, they represent the same student. There's some redundancy in the student database. We can or maybe even should drop one of the two records. Whereas we cannot say reasonably assign a total order and say this student is larger than this small student in any reasonable sense, unless we enrich student records, and this is what universities, of course, do all the time, namely add an additional field with a student ID. Student IDs can be compared, say one student ID is larger than the other or smaller than the other. Thus, this is kind of a mathematical explanation for why student records usually are amended with a new field, student ID, in order to use that in order to unique student ID in order to impose a total order. So, and if we have such a total order, then we can now specify the neighborhood search problem. But first, we also reflect that total order in our choice of primitives. Now we cannot only compare for equality and non-equality, but now we can ask whether one element is less or equal to the other or not. So one question that I've received, interesting question, is in order to recover the previous case where we could only compare for equality, now equality can and has to be expressed as two of these comparisons, namely x equal y means x is less or equal to y and y is less or equal to x, so that technically this is not the same as the previous case, because now we have twice the cost in order to kind of simulate equality comparison using two of these less or equal comparison. But since we're only interested in asymptotic cost, it doesn't really matter much if we assign cost 1 or if we assign cost 2 to this ordered comparison. Yeah, constant cost for each of these operations. This is what will matter when we analyze algorithms, and that's what we're going to do. But now we also add the hypothesis that the input data, the input sequence, the input array already be sorted. The elements must occur in strictly increasing order. And that naturally raises the question, how can we create such a sorted array from an unsorted one? That's a very important question, which I would like to postpone, however, to chapter 3, when we talk about sorting algorithms. And for now, we only suppose that the data already is sorted, perhaps because the user has provided it in increasing order, or maybe we already have run a sorting algorithm. Also observe that here we require the data sorted to be strictly increasing, so no repeated elements are considered for now. We will relax that condition also in a minute. So, and with that condition, we now can resume and finish the problem specification, namely the output should be an index, a natural number of elements, such that these two elements in the input array kind of bracket, include, and embrace the element y we're looking for, in the sense that right, xn should be less or equal to y, and y should be strictly less than xn plus 1. So such an index n should be output, and before proceeding, we should make sure that this problem specification is well defined, right? Yes, so problem specification is an important part of algorithm design and analysis, and it can be quite subtle to make sure that such an index n only exists, and it does, based on our hypothesis that the input sequence already is sorted in strictly increasing order. Also, there's a case when y could be much less than all the elements in the array, not only, right? So the first generalization is now, even if y does not occur in the input, among the input data, then still the algorithm is required, algorithmic solution is required to output some index, namely of elements, kind of including and embracing y. So more information. And if y is less than all elements in the array, then the output index s is indicating of that, because remember, we're starting to our arrays with 1. So x0 is kind of an implicit sentinel with the value minus infinity. Right. So let's make that explicit. x0, the sentinel is supposed and not stored, but considered as having my value minus infinity, and xn plus 1, again an element which is not really part of the array, is supposed or considered to be infinite. So if y happens to be larger than all elements in the array, then still the specification is well defined. In all possible cases, there's a unique index n from 0 to n that satisfy that. So that's important mathematical considerations prior to even starting designing algorithm for that neighbor search problem, which we're going to do next. And the algorithm is kind of straightforward. First, we compare the first element in the array. If that is larger than y, then means that y, we're in the first exceptional case, we need to output the index of the sentinel 0. Otherwise, walk through the array to check when the first time y is kind of dominated with respect to the total order. And the first time that happens, then that means we have located the position where y is kind of bracketed in between, and we return the index of the left part of the bracket n minus 1. And if we walk through the entire array without finding an element that dominates y, then that means we're in the other case of the sentinel. Now y is greater than all elements in the array, and we need to output capital N as indicator of that. So that's our algorithm, and let me reiterate, the algorithm itself is kind of trivial. What is want to convey here is our examples of specification, making sure it's well specified, and capturing all the primitives that occur, that are used in the algorithm design and analysis. So correctness is again trivial, and also running time here is trivial. It's linear running time walking through the array, and that's optimal because all elements in the array maybe have to be looked at, or is it? Can we do more efficiently than linear running time? Well, actually we can, because now we have the hypothesis that the input data is provided in increasing order. And that's where binary search comes into account. You probably know binary search, but so let me recall binary search, but also adapt and adjust the problem specification, taking into account the hypothesis that we know. So here, binary search, input is the same as before, array sequence, but now it can be not necessarily strictly increasing, but instead in non-decreasing order. So we relax the requirement compared to the previous slide. Now it's only non-decreasing. In particular, there can be repeated elements. So we want to make sure that the problem is still well specified in this case. And the problem specification asks to output an index, the index of the smallest index, such that y is less than the element at that position. That again always exists based on our sentinels, right? And now we can move on to the algorithm, which uses this ordered comparison. And the algorithm binary search maintains kind of a left bound and a right bound. Left bound and right bound between the element y, which we're looking for, is or should or would be located between the left and the right bound. And initially, the left and right bound are initialized to encompass the entire interval, going from 0 to n plus 1, including our two sentinels. And this is something kind of that binary search maintains as a loop invariant, namely that y, if it exists or where it exists, is always contained between xl and xr. And then L and R are kind of move closer and closer to each other until finally they refer to where y would have been located to the x RNA. So as long as the subinterval where I is or would be located has positive length, as long as the right end of the interval is strictly beyond the left end, we're going to take the middle position of that subinterval. That's the middle position, the arithmetic average position, round it down in case that's not an integer, in case we're having some fractions, and then compare the element at that position to the one we're looking for, right? And if the one we're looking for is smaller than that, then continue with the right half of right subinterval. That means the left half of the subinterval. That means replace the previously right bound with a now decreased middle point, with a decreased bound, the new middle point. Otherwise, repeat the binary search in the right half of the interval, right subinterval, now with the meaning that now the left index is replaced with a new middle element index. So that's binary search. And this time, as opposed to the previous algorithm, correctness is maybe a little bit more subtle. So why is that correct? And to see and assert correctness in this case, we state and maintain the following loop invariance, that y is always greater or equal to the element at the left boundary and strictly less than the element at the right boundary. So this is certainly true initially, right? When L is equal to 0, that's our left sentinel, and R is n plus 1, that's our right sentinel, which is plus infinite. So y is really between both of these initially. And this is kind of like the induction start to a mathematical proof by induction. And the induction step will assert that if this inequality holds before the loop body, then after one execution of the loop body, it will still be true. This is something I would like you to verify. And this is where this rounding, for example, rounding down comes into play. We cannot exceed the array bounds, right? The array ranges from 1 to capital N. Make sure that this rounded down arithmetical average is again between 1 and capital N. And based on these two conditions, that after one execution of the loop body, which has replaced one of the two bounds, R or L, based on this condition, then still this loop invariant is still valid. And once you, please do it, once you have verified that, then it follows by mathematical induction that also at the end of the loop invariant still holds. It does initially induction start. It maintains being true throughout the loop execution. So at the end of the loop, it will still be true. However, another subtlety we do need to prove is that the loop indeed does terminate. And that again is in this case not hard to see, but it's important to verify to show that the distance between the right and the left end of the subinterval, the difference between R and L, decreases. It is roughly decreases by a factor of 2 in each loop iteration. More precisely, we have the following equality after one loop iteration. The new right and left bound, R prime minus L prime, is at most the previous interval bounds R minus L divided by 2, rounded up. And please verify yourself where we do need to round up. It is not true if you do round down. But even with rounding up, the number of iterations performed by the loop, if the distance between left and right bound interval and decrease by a factor of roughly 2, then it means the loop can make at most a logarithmic number of iterations, and thus we can derive this asymptotic running time bound log n following from our correctness and from this running time analysis using mathematical induction. So yes, correctness and runtime analysis according to our paradigms of algorithm design and analysis for the case of binary search. Okay, so let's now move on and consider the uniqueness problem. Again, first specifying the uniqueness problem, then agreeing on which primitives we consider and what is the computational cost of these primitives, and only then start to devise and analyze algorithms with respect to correctness and asymptotic computational cost. So what's the specification for the uniqueness problem? Input is the same as previously, but now the output is supposed to be a Boolean, true or false, or in numerically 1 or 0. And 1 true means that all elements in the input are pairwise distinct. There's no repeated element in the input. And 0 means that there is a repeated element. At least one element occurs twice at two different positions, y and j, are integer indices, different integer integers, but the elements stored are equal with respect to our, we don't need a total order here, just equal, for example, as student records. Imagine, for example, that by some kind of accident, the same student record occurs twice in the university's database. That is something that the uniqueness would detect. Now we want to design an algorithm for that uniqueness, and actually we're going to design 3 algorithms of increasing efficiency. First algorithm is kind of trivial, just check this logical condition, or this logical condition, the negation, using 2 loops, one for I and one for j. That's our first algorithm. You see that here, I and j, and what you see here is, yes, I ranges through all possible indices except for 1. The case I equals 1 need not be considered because we're only interested in I and j that are distinct. And so in the case where j instead starts at 1, so we don't need to cover the case 1 for the first index. On the other hand, j only needs to run up to I minus 1. J equals y is not interesting. These are not distinct indices. And the case where j is greater to y does not need to be considered either, because by symmetry, then we could just replace the roles of I and j mathematically. Well, algorithmically, it doesn't make much of a improvement. It's only a factor of 2, right? So which is ignored in our asymptotic analysis, but it also simplifies the loop a little bit, right? In the loop body, so 2 nested loops, and the loop body will simply test that condition. And if 2 elements are found to agree with distinct indices, then the search will stop here and indicate that there is an repeated element. It will not continue searching for possible other repeated elements, but only once the first repetition has been found. If no repetition is found throughout both loops, then we can be sure that there is no repetition at all, and the algorithm unique 1 will return indicator 1. So that's algorithm. It's obviously correct, and the running time is also quadratic because we have these 2 iterated loops, which both run for at most capital N iterations, and that is also asymptotically tied, because whenever y is greater than n over 2, which happens to half of the iterations of the outer loop, then j must run up to at least n over 2, which is the second loop. So we have in our analysis, we can identify two subloops, nested subloops, each one being repeated n over 2 times. And thus these subloops alone kind of contribute to the up to this factor of 1 over 4 to the quadratic running time. So the running time analysis is asymptotically optimal. It's somewhere between n squared over 2 and n squared over 4. Anyway, it's n squared. Correctness is trivial, as we saw. So now the question arises, can we do better? Right, so the input array has linear size, but we have 2 loops. Do we really need the 2 loops? And let's now answer that question. We're going to return to that question when we talk about the sorting problem, but for now, let's simply change the specification of the problem and require that the set of elements we're considering and comparing is now equipped with the total order and is actually already sorted in non-decreasing order. With that increased hypothesis, we can design a more efficient algorithm that only needs to compare adjacent elements, right? Because if there is a repeated element, then it must be adjacent according to the non-decreasing hypothesis, right? So that means it gives rise to our second algorithm that has only one loop. So it's a linear time algorithm and it compares all adjacent elements. And if 2 adjacent elements agree, then there's a repetition. If no 2 adjacent elements agree, then there's no repetition based on this additional hypothesis of the problem specification, our second algorithm. Okay, that being said, let's now move on to the third algorithm. And in the third algorithm, we're further adding a further hypothesis, namely the hypothesis that the data we're operating on is not just an arbitrary set, not just an arbitrary set with a total order, but even more strong hypothesis that it is the set of consecutive integers from 0 to m minus 1, where m is some fixed number. So in the previous case, that would apply well to student records. The previous case with the total order would apply to student records with some total order. It could, for example, be the lexicographical order on student names, right? That's a total order. That's the whole point of having a lexicographical order. But now, if we require that the data be integers, and student names with lexicographical order is not integers. Instead, we suppose that the integers can be applied to the case where the student records consist of student IDs. Student IDs are integers, and the benefit of having integers is not that they not only do they form total order, they do, but we already had that in the previous case with the lexicographical order on names. But moreover, these integers can be used as array indices. So now we can access the semantics of an array access changes. That's what you see here. Namely, now the semantics of access becomes an iterable access function. So namely, the result of an access, accessing the nth element in the array, results not just in an arbitrary element from the array X, but results in turn in a natural number, which can then in turn be used for array access, right? So here you see that illustrated. So we have our input array with indices ranging from 1 to n. And now we consider our third algorithm, which is going to be even more efficient. Namely, it is going to use another array. This time the array indices start with 0. Minor technical detail. You can, of course, change that to also range from 1 to capital M. But anyway, and this is supposed to be initialized with 0, that is with Boolean value false. And that it means to check whether the data with the item M has already been detected or not. That's the idea behind this array present. The algorithm will, here you see the array present with indices ranging from 0 to m-1. And the algorithm will maintain that array and update that array, indicating whether the data item small m has already been found among the input array or not when walking through the input array. So the algorithm walks through the input array and then looks at each element in the input array at position n, and then uses the iterable access to consider the data at position n in turn as an index to the second array, this array. And then look at that array position, and if that has already been marked as present, then that means this is the second time the algorithm sees the data x of n, and thus returns 0 and stops searching. It has found a repeated element. It does not say where the element has been found, but it does know that the element had been found before and is now found a second time, so there has been a repetition. So let me emphasize that subtlety in the specification. We're not, the algorithm is not required to return such a pair I and j where an element recurs twice, but only required to indicate that the element is occurring, an element is occurring twice. And that's what this algorithm is kind of exploiting, and indeed returning 0, this indicator. If the element has not been marked as already occurring, then the algorithm will now mark it as recurring. So again, using this iterable access, the element at position x of n is used as index to the second array, and that array position is now marked as occurring, putting that mark. So if such an element is found again later during the execution of this loop, then the first case will hit it. Then later, then that repetition will be detected and reported. Otherwise, this is kind of like charging that indicator. And at the end of that loop, if that loop runs through all the input data without detecting such a repeated occurrence, then it reports that all elements indeed are distinct. It will report 1. So that's our third algorithm for the uniqueness problem, this time with the additional hypothesis that the data being processed constitutes of integers, and not only of arbitrary integers, but integers of a certain range from 0 to m-1. And the latter, mathematically, there always exists such an index capital M, right? But here, two important assumptions are made implicitly. And first, that such a capital M is known to the algorithm. It must be fixed before in order to create this helper array present and initialize that in that line. So capital M must be known. And secondly, capital M should be, in a sense, small, because if you analyze now the algorithm, the running time is linear. That's optimal, right? We cannot do better. But now the memory, let's have a look at the memory used by this algorithm. And this memory is really dominated by this helper array, which has a capital M entries, booleans, bits each, but a large number of them. So if capital M is large, then that means that algorithm uses a lot of memory. So far, we've been ignoring the aspect of memory use and focus on runtime only. But this is an example where really memory use becomes maybe crucial. For example, if capital M, maybe the set of data we're operating on consists of, let's say, machine integers of 32 bits length, then that means capital M is 2 to the 32. That means the helper array will occupy something like a memory in the order of gigabytes, right? 2 to the 32, that's gigabytes. So that's a huge amount of memory overhead compared to the input array, which could be much smaller actually, right? If it's like students, university maybe has 10,000, 20,000, 30,000 students, but if the student IDs are the machine integers, then that algorithm would use a lot of too much memory, unreasonable amount of memory in order to arrive at the linear running time compared to the previous algorithm, which had maybe less efficient in terms of time, but much more efficient in terms of memory. And yeah, separate courses, for example, on parallel computing, might want to consider additional measures of efficiency, such as communication volume or number of processors or CPUs used. But here, let's return to the focus on the question of running time and memory use. So how can we improve the memory efficiency for this uniqueness problem? And this is what we'll close with today. Namely, hashing is a common method for that purpose. And for hashing, we again change the problem specifications only slightly. We now suppose that the data starts with 1 instead of 0. That's a minor distinction, but I do want to point that out. And also the primitives are now changed. Now we suppose that we can actually do arithmetic on the values, right? So that the values are integers, it means mathematically arithmetic makes sense. And we suppose that these arithmetic operations, addition and scaling, are available as primitives. Right. So for example, student records, as I emphasized, cannot be added or scaled, but student IDs can be added and can be scaled. They might not result in another student's ID, but that's the whole point exactly of the uniqueness problem, to see whether it does result in another student's ID or not. So now that the problem specification has been updated to cover hashing algorithms, and in particular the choice of primitives has been updated. Let's consider hashing, and the idea behind hashing is to use another array of present indicators. So we previously had this in algorithm unique 3. We had this large array, helper array, which incurred a large amount of memory. Now we consider an additional array, but a small array, helper array, which is called Y. And the idea is to kind of map the large array to this small array, because intuitively, if the input data items, capital N, is much smaller than capital M, then yeah, we should be able to get away with much less of a helper data than capital M. Recall the example of student IDs, where N, the number of students enrolled, is maybe at most 50,000 even at a large university, but the student IDs can go up to 32-bit integers, maybe even 64-bit integers. So that's the idea, to map that large array, helper array, onto a smaller array and then get rid of the larger array totally. So these are the two steps we want to consider. Here you see this smaller helper array, now helper array of size p, with indices ranging from 0 to p minus 1. And I'm going to tell you in a minute what capital P is. The idea is it should be much smaller than capital M, but a little bit larger than capital N. So that's kind of the trade-off we want to create and explore. Much smaller than M, the data items we're considering, but larger, maybe linear or polynomial in capital N, the number of data items we want to we receive. And whereas the intuition is to map this large array, helper array, onto this smaller helper array in the first step. And in the second step, get rid of this large array entirely and only consider the small array. So how do we map this large array to a small array? This is what this hashing is about. And here we consider one kind of example hashing, which is known as division hashing. So in division hashing, the mapping from the large array to the small array positions, I should emphasize, large array position to small array positions, is this multiplying the input index x with some constant k, some integer, and then take the result modulo capital P. And observe that this indeed maps the large array position to the small array positions when x ranges from 0 to capital M minus 1, then x times k ranges from 0 to k times m minus 1, which is even larger, but then taking the remainder, the modulo with capital P, results in some integer from 0 to p minus 1. So that's well-defined, again, a mapping from these array positions to these array positions. And also observe that these array positions are kind of, how to say, folded back into that array with some kind of jumps, right? So in steps of small k, right? So this maps to 0, this maps to k, this maps to 2k, 3k, and so on. And then when reaching the top of that small array, it starts over again. So that's the idea here. Okay, that's our class of hash functions in plural, because we're going to consider different choices of small k, and actually we're going to choose k randomly for reasons that become clear later in our randomized analysis. So here's the idea how to create the smaller helper array, that capital B be a prime number that will be mathematically relevant, and it should be larger than capital N, maybe linear or polynomial in N, but not too much larger. At the same time, it should be much less than capital M. And then we guess a random integer k from 1 to p minus 1 here in this hash function. And for those of you familiar with number theory or algebra, using capital P as a prime number and considering integers modulo prime means we're talking the set of residuals forms a field. It allows for division, for example, except for the 0 element, which we exclude here deliberately. That will become relevant in the analysis. And now we can finally state the algorithm. The algorithm is a linear time algorithm. It uses one loop, one walk through the array, and then, as previously, considers the entry in that position. And now it uses the additional enhanced primitive, being able, supporting arithmetic on these values, the array entries, namely multiplying with this k, right? Multiplying with k and taking the modulo, the remainder, with respect to capital P. So that's the operation we use here, right? Which is permitted according to the primitives. And that's an index into the small second helper array that is going to be used, namely checking whether this helper array position there already exists. The entry we're currently looking at, we're looking at entry xn. And if that entry has already been occupied in the helper array, then it means we have seen that element before. The algorithm has seen that during any previous iteration of the loop. It doesn't know which one, but we're not supposed to report where the element has been repeated, only that it has been repeated. And this is what the algorithm does in this case. Otherwise, it marks that marks that entry here as occupied. More precisely, it occupies, it copies the element of the current position xn into this place and then repeats the loop. Well, that's what you see here. Except there's a subtlety here, namely, remember that the hash function mapping from indices in this large and now only virtual present helper array to the actual physically present smaller helper array, that this hash function is not injective. It cannot be injective. That's the whole point of mapping this larger array onto this smaller array and then getting rid of the larger array, that now several values here, several positions are going to be mapped to the same position here, right? So for example, when x is equal to 0, or when x is equal to capital P, or when x is equal to 2 times P, each time the result of that hash function will be the same, it will be 0, right? Let me say that again. This entry gets mapped to here, the pth entry gets mapped to here, the 2 times P entry gets also mapped to here, and so on. Many entries get mapped to here to the same position, because P is by choice much smaller than capital M, so many multiples of P occur here. So that means that this test is actually possibly incorrect, right? It could happen that the element at 0 has resulted in being marked here, but we're currently looking at the element P, then this return is actually incorrect. Moreover, it could happen when we mark that position now as marked, that it already has been marked. And this is why there's a second loop inside, which is kind of the purpose is to handle such so-called collisions. So let me explain that further. So the algorithm kind of disposes of the previously large helper array, and it instead jumps directly to the smaller helper array. That's what you see here, right? So the element entry at position x of n is then processed with a hash function. You see that hash function here, and then that's where we look at in the smaller helper array. And if that position is already occupied, then the algorithm performs collision management and looks at the next subsequent position. That's what you see here. So let's analyze that division hashing algorithm. The memory consumption has now been improved to big O of P, right? We've got rid of the big helper array, and now here's only capital P. But what about the running time? Well, there's a linear running time here, but there's this nested loop here, the while loop, which is hard to predict superficially how often that is being repeated, right? Furthermore, there's a question of correctness, right? So even if the two hash values coincide, that doesn't necessarily mean that the values coincide. So the algorithm could erroneously report as repeated two entries which are not actually equal, but only their hash function values are equal. So correctness is also a big question. Yeah, with that, we're going to look into that more closely on the next time. So for now, let us stop here and announce that next time we're going to recall division hashing, and we're going to look more closely at collisions, how the algorithm handles collisions, and how often collisions can occur, because both affect the correctness and the running time. So that's all for today. Thank you very much for your attendance, and we're going to see you again next time.